Okay, so this video is meant to go over the concept of resistors in parallel. And resistors are in parallel is when there are multiple resistors that lie along separate paths in a circuit. So in this one, the current can split up and go down different pathways. So if you were to think about the actual circuit with the light bulbs, here's your power supply, and so you'd have a wire that's coming out of your power supply, and then you'd have like this junction point here, and it would split, and so one path would go to this light bulb, one path would go to this light bulb, one path would go to this light bulb, and then each of those light bulbs would have another wire that goes back to kind of a communal path, and that path leads back to the power supply. If you were to draw this with a circuit diagram, then here's your power supply. The wire comes out. Right here is where it splits. There's one path, two paths, three paths. They come back together and they go back to the power supply. Or you could also draw it this way. I'm not a big fan of drawing it this way, but this is where that kind of the name resistors and parallels comes in, where you have a path that splits, and then another path, and then it splits, and they all eventually come back together, okay? So the thing with this is that the current is going to come out. So if this is my current value, my total current comes out of the power supply, and then when it gets here, it splits down the different pathways, and then it comes back together, because remember the rule is you can't lose current. So current can split up and go into different pathways, but then it eventually must rejoin and then come back together. Okay, so in terms of like our rules, the current splits up to go down different pathways. So I total in this case is going to equal I1 plus I2 plus I3 plus dot dot dot. So this is a little bit of a different relationship than what we saw with resistors in series. For resistors in series, the current was the same through each resistor. For resistors in parallel, it's going to split up. Now in terms of what's happening with the voltage, let me bring this board and draw like my circuit nice and big. So here's my parallel circuit, and for the ease of explanation, we're just going to say that these are all the same resistance. Resistance 1, resistance 2, resistance 3. And we're going to say it's a 12-volt power supply. So remember, I have my little charges here. They're super energetic. Oop, they're happy, huh? They're coming out of my power supply. And remember, they're coming out of the high voltage side. So they have 12 volts. So they come out here, they come out here. Here they are, and here they get to this junction. And so when they get to the junction, they split up, because that's what the current does when it gets to a junction. So some of the current goes this way, some of the current goes this way, and some of the current goes this way. Now, when I think about what they're going to look like on the other side of these resistors, remember, this wire here, this wire is a low voltage wire. It's 0 volts. So anything touching this wire, because this is touching that side of the power supply, anything touching this wire has to be 0 volts. 0 volts, 0 volts. When these guys get through this resistor, they have to have 0 volts. They're super sad and not happy because now they have 0 volts. So what this shows us is that for resistors in parallel, they have the same voltage dropped across them. Okay? So for resistors in parallel, the voltage across resistors in parallel is equal resistors are in parallel with the power supply, the total voltage will be equal to the individual voltages. So if the resistors are in parallel with the power supply, meaning like they are on their own path with the power supply, then the total voltage of the power supply is equal to the individual voltage of each resistor. The total voltage of the power supply is equal to the individual voltages of the resistors. So the total voltage would be equal to voltage 1, equal to voltage 2, equal to voltage 3, etc. So the two relationships we have for resistors in parallel is this one here about voltage and this one here about current. Okay? And just like we did with resistors in series, we're going to use these two relationships to look at a relationship for the total resistance for resistors in series. So I'm going to go through a derivation. Again, you can write this if you want. I will tell you at the end what is important to write. Get rid of my drawing there. So the first relationship that we're looking at is this concept that I total was equal to I1 plus I2 plus I3. And remember Ohm's law. Ohm's law is the key to this. Ohm's law says that I equals V over R. And remember that as long as my subscripts are in agreement with Ohm's law is true. So I total can equal V1 over R1, I1 can equal V1, lies. I total is equal to V total, R total, and I1 would be equal to V1 over R1, I2 equals V2 over R2, etc. Okay? So if that's true, then I can insert this relationship into this equation. So instead of writing I total, I could write V total over R total. Instead of writing I1, I could write V1 R1. I could write V2 over R2, and then V3 over R3, etc. Now remember that for resistors in parallel, let me bring this down, for resistors in parallel, this is true, that all the voltages are the same. So if all the voltages are the same, then I can cross them out. Boom, 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 boom. And I can get that 1 over R total is equal to 1 over R1 plus 1 over R2. This is kind of a weird relationship. It's an inverse relationship. So this is kind of the summation of resistors in parallel. So I'm going to kind of bring that to this board here. So resistors in parallel combine as inverses. So 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus blah, 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 blah. Another way we could write this, and we did this when we did lenses, is we could say that the inverse of R total is equal to the inverse of R1 plus the inverse of R2 plus the inverse of R3, etc. And something to note is that when we had resistors in series, that the more resistors I had in series, then the more resistance I had. Like my resistance just kept getting bigger and bigger and bigger. But when resistors are added in parallel, the total resistance drops. And it's because you're providing more paths. And if you provide more paths, you provide more opportunities for charges to leave the power supply. And so you're reducing the resistance. It's like if you had like a really full gymnasium and you only had one door open that people could exit. That's a high resistance. And so there's not gonna be a lot of people flowing out of the gymnasium. But if instead you open multiple doors, now you're having multiple paths through which they can exit, and so a lot more people can get out because there's a lot less resistance. Okay? So now we're going to go through and look at some mathematical examples of resistors in parallel.